Welcome back, everyone. We're in chapter 14 today, and this is on acids and bases. Um, you're going to see that acids and bases are one of the most common chemical reactions in all of the universe. It happens all the time in your body. It happens all the time in the environment. And so this first section, I'm going to have to define what they are so that you can recognize when you see them, and you actually see them all the time. So let's look at some examples. So anything that's sour, like lemons, or the tang in cheese, like in Parmesan cheese, or in Coke, or in oranges, anything that's got that kind of a zippy to it, is acidic. So citric acid is what's in all soft drinks. That's acidic. Vinegar, that's acidic. So acids are always used in food. It gives taste, but it also is doing some chemistry inside their food to make all these compounds that we think of as delicious. Okay, so let's first of all define them. I'm going to give you an old definition first, and then later in another lesson we'll give you a more updated idea of what an acid is. A chemist named Arrhenius, back in the 18th century, came up with the original definition of what an acid is, as he looked at different things and said, "What is it that's causing this to be acidic?" He proposed that what it was a proton. A proton is a hydrogen ion. So remember, hydrogen has one proton, one electron. If the electron is taken away and it becomes an ion, then it's a positive one ion. So an acid, according to Arrhenius, is anything that can donate a proton or anything that can donate a hydrogen ion. So look at this example of hydrochloric acid. It's obviously an acid. It's named an acid. And hydro here being the hydrogen is the metal, in this case, of a nonmetal chloride. If it were to dissociate, and that's one of the things that you're going to see that acids do is they dissociate. So that's what this is. They're electrolytes. They dissociate into charged particles. So if you were to put this into water, they break apart as electrolytes, and you're going to have hydrogen ions in aqueous, and you're also going to have chloride ions in aqueous. So according to Arrhenius, any acid donates protons. If you put them in water, they dissociate completely. They're very strong. Okay, they are sour. If you were to taste it, the idea of a lemon, that's the acid that you're tasting in a lemon. Litmus paper, which is made out of an organic chemical, like a dye. Actually, it's a dye. If you were to take red litmus paper and put an acid there, or take blue litmus paper and put an acid there, it turns it red. So that's an indicator that we use in the lab a lot that nobody else cares about. And it also neutralizes bases. So we're going to see that acids and bases will actually cancel each other out in a lot of ways. It's kind of cool. We'll talk about it later. So we need to name them. If you have an acid, you're always going to have a hydrogen. The hydrogen at the beginning is indicating that you've got an acid. So H something you can guess is an acid. If you have the something is simply a simple nonmetal ion, like anything from group 2 or I'm sorry, group 7 or group 6, group 5, any of those, you're going to use hydro in the name. So this is chloride, and so it's going to be chloric acid. And if it's just a simple, simple ion, nonmetal ion, you're going to use hydro in the name. So it's hydrochloric acid. Okay. The ic is what you're going to call most acids. Most acids are going to be ic. There are some acids that are not, and we'll see when they're not. But if you have a simple situation like this, you're going to call it ic, chloric, and it's hydrochloric acid, HCl. Here's the same one. This is in group 7 also, hydrobromic acid. And one of the polyatomic ions that follow this same naming pattern is with cyanide. So CN, if you remember, carbon and nitrogen together as a -1 ion was cyanide. So hydrocyanide goes to hydrocyanic, cyanic, how about that? Acid. Okay, so you're going to take whatever the nonmetal is, turn it into ic, and then have hydro in front. If you have a polyatomic ion, especially one that has oxygen in it, remember an oxygen polyatomic ion had a couple different names. So if you have more oxygen, we called it 8. So NO3 negative 1 is nitrate. NO2 negative 1, the lesser number of oxygen, was nitrite. Okay, so in this case, you're going to have to remember something. If you have the higher number of oxygens in an oxyacid, so this is meaning it's an acid with oxygen in it, okay, you're going to have, in this case, nitrogen and oxygen, or sulfur and oxygen. You're going to have the larger number, the nitrate, turns into nitric acid, so what we would call the common acid, nitric acid. If you have the lesser number of oxygens, the nitrite, we have to distinguish an acid used with a nitrite from an acid used with a nitrate, because HNO3 is a different stuff than HNO2. So we have to have a different name for it so that you can distinguish it. So the larger number, whatever 8 was, is going to go to ic. 8 goes to ic. 8 goes to ic. You have to memorize that. Ite goes to us. So nitrite ion goes to nitrous acid. Nitrous because the NO2 was nitrite, and it becomes nitrous. Here was sulfate and sulfite. Sulfate SO4. Sulfite, which we did not learn, but it should make sense to you. SO4 is the 8. That's the normal one, the most common one of polyatomic ion with oxygen. And then one that had less oxygen goes from 8 to ite. So 8 goes to ic. So sulfate, hydrogen sulfate, is not considered, you don't call it hydrogen sulfate. Instead, you call it by its acid name, sulfuric acid. Now notice that this is not hydrosulfuric acid. This is SO4. This is a polyatomic ion. It's not a simple nonmetal ion. So we don't say hydro. We just use its ic name and we're done. So this is sulfuric acid. The SO3, which is sulfite, can't be sulfuric, so we need a smaller name for an acid. So the lesser number of oxygens in an acid is us. So this is H2SO3 sulfurous acid. Here's another example, chlorate. Remember, chlorate had the higher number of oxygens. Chlorite was the lower number of oxygens. So 8 goes to ic, ite goes to us. So this is chloric acid, chlorous acid. But you also remember that with chloride and bromide joining with oxygen, there were 4 forms. 4 forms of this. So you had perchlorate, that was the largest number. And then the next number down of oxygens, we had chloric. And then the next number of oxygens down, we had chlorite. And then the lowest number of oxygens, we had hypochlorite. It works exactly the same way with this. You're going to have chloric acid, perchloric acid, chlorous acid, that's the ite, and hypochlorous acids. So the ite with the hypo, so this is the lowest number, hypochlorous. The next number up, chlorous. The next number up, chloric. The next number up, perchloric. The next number of oxygens, what I mean. So here's some examples of that. You can pause the tape and look at this. This is an excellent resource. All right, I'll see you in class.